Welcome to another deep dive. We're looking at a phenomenon today that is literally flowing right through your home at this very second.
Yeah, right out of the tap.
Exactly. So
Mm.
just consider your daily routine for a moment. Have you ever pulled a drinking glass out of the dishwasher only to find it coated in that cloudy, persistent film?
Oh, yeah. The worst.
Right. Or perhaps you've noticed your home coffee maker struggling to brew. The water flow is slowing down, the pump sounds like it's straining, and the temperature is just fluctuating wildly.
And our instinct is always to just blame the hardware.
We do. We
Yeah.
assume the appliance has just, reached the end of its life cycle. Time to buy a new one.
But based on the stack of research we're examining today, the real culprit is usually something completely invisible to the naked eye.
It's totally invisible.
Yeah.
And the source material we were working with today comes straight from the U.S. Geological Survey, the USGS.
Yes, they're comprehensive water science publications.
We're specifically looking at their rigorous studies on what is classified as the hardness of water.
It's a pervasive issue in municipal and private water systems alike. When appliances fail, we always look for mechanical faults. But the data indicates we really should be looking at the chemistry of the water itself.
So the mission for this deep dive is to unpack exactly what hard water is at a molecular level, uncover the thermal and chemical mechanics of why it systematically sabotages our appliances, and evaluate whether this well-documented nuisance might paradoxically offer a tangible health benefit to you.
Which is a really surprising twist, honestly.
It is. I mean, we all know hard water is rich in dissolved calcium and magnesium, but the USGS data reveals something fascinating about the specific geographical and chemical journey those minerals take before they ever hit your water heater.
It demands a massive shift in how we perceive tap water. We tend to view water as a static, inert utility, right? Just pure H2O.
Right, just a clear liquid.
But the USGS material illustrates that the water flowing from your tap is actually a highly complex dynamic chemical solution. It's been interacting with the Earth's crust for decades, sometimes centuries, before it reaches you.
Okay, let's unpack this. We already understand the baseline water hardness is just the measure of dissolved calcium and magnesium.
Correct.
But the USGS text leans heavily into this concept of water as the universal solvent. So how does that principle actively dictate the mineral composition of our groundwater?
Well, what's fascinating here is the specific mechanism of that solubility. Water is a highly polar molecule.
Meaning it has a slight positive charge on one side and a slight negative charge on the other.
Exactly. It's like a tiny magnet. And as precipitation falls from the atmosphere, it picks up carbon dioxide, which creates a very weak carbonic acid.
So the rain itself is slightly acidic.
Yes. And when this slightly acidic rainwater percolates through the soil and into the bedrock, that polarity and acidity just go to work. It acts as a relentless solvent.
Just slowly eating away at the rock.
Slowly but surely. In regions where the bedrock is composed of sedimentary rocks like limestone or dolomite, which are packed with calcium carbonate and magnesium carbonate, the groundwater just dissolves those minerals. It integrates those ions directly into the water supply.
Which means the water sitting in a subterranean aquifer is essentially a liquid snapshot of the surrounding geology.
It's liquid rock.
Liquid rock. And when a municipal well or a private pump draws that water up, it is delivering that dissolved rock straight into your plumbing.
Straight into your house.
And the most immediate tactile evidence of this geological delivery system is what happens when you just try to wash your hands.
Right.
The USGS sources detail the chemical reaction that occurs between hard water and cleaning agents. And it's not great.
The reaction is actually quite aggressive. Traditional soaps are typically sodium or potassium salts of fatty acids. When you introduce those sodium-based soaps to water with high concentrations of dissolved calcium and magnesium ions, a displacement reaction occurs. The calcium and magnesium ions essentially kick the sodium ions right out of the soap molecule.
They just swap places.
They do. And the resulting compound is what we colloquially call soap scum.
Ah, okay, that's what that is.
Precisely. The chemical term is calcium stearate, or magnesium stearate.
And unlike the original soap, which is highly soluble in water and washes away cleanly,
Calcium stearate is an insoluble precipitate.
meaning it won't dissolve.
Right. It is a solid, waxy substance that clings to surfaces. Your skin, your bathtub, the fibers of your clothing.
So it's not merely that the water is failing to rinse the soap away. The water is actively engaging in a chemical reaction that destroys the soap's surfactant properties and creates a stubborn new residue.
Yes. You're actually making a new solid compound right there in your sink.
Wow. So if the soap is actively binding with the calcium and dropping out of solution, What does that mean for the practical application of cleaning, like doing laundry?
It creates a compound inefficiency. First, a significant portion of the detergent you add to a washing machine or dishwasher is immediately neutralized just by interacting with the minerals in the water.
It's sacrificed to the calcium.
Exactly. That means you have to use a substantially higher volume of detergent just to reach the baseline concentration required to actually clean the clothes or the dishes.
You're just wasting soap.
And second, that insoluble precipitate, the soap scum, embeds itself into fabric fibers. It causes them to become stiff, gray, and brittle over time.
The destruction of cleaning agents is frustrating enough, but the data indicates the situation escalates dramatically when we introduce thermal dynamics.
Oh, absolutely. This is the appliance killer.
This is where hard water transitions from a chemical annoyance to an active threat to your home's infrastructure. So let's examine the mechanics of what happens when this mineral-rich water is heated in a water heater or a coffee machine.
This is where we see a phenomenon called retrograde solubility.
Retrograde solubility. Okay, break that down for us.
For most solid substances, solubility increases as the temperature of the water increases. Think of dissolving sugar in hot tea versus iced tea.
Right. Hot water holds way more dissolved sugar. It melts right in.
Exactly. But calcium carbonate behaves in the exact opposite manner. As the temperature of the water increases, calcium carbonate becomes less soluble.
That is a critical distinction. So the heat is actively forcing the dissolved rock out of the solution.
It is precipitating out. When the hard water hits the heating element of your coffee maker or the interior of your household water heater, the thermal energy causes the calcium carbonate to drop out of the aqueous phase.
It just crystallizes.
It crystallizes onto the nearest solid surface. This solid, rock-like crystallization is what the industry refers to as scale.
And once that scale begins to form on a heating element, it fundamentally alters the thermal efficiency of the appliance.
Right.
Because mineral buildup inside a coffee maker isn't just unsightly, it's an insulating layer of rock separating the heat source from the water.
That insulation effect is the root of the appliance failure. The heating element has to work twice as hard. It's running hotter and longer just to push the same amount of thermal energy through the layer of calcium carbonate scale and into the water.
So this is why a scaled-up coffee maker takes twice as long to brew and often produces lukewarm coffee.
Exactly. The machine is essentially suffocating itself with geology.
Suffocating with geology. I love that. And here's where it gets really interesting. The USGS documentation doesn't just outline the problem. It provides the scientific foundation for a highly common, yet often misunderstood, household solution.
The vinegar trick.
The vinegar trick. People have been running white vinegar through sputtering coffee makers for decades. It's treated like this old wives' tale, but
Yeah.
looking at the chemistry, it is a highly specific, targeted reaction.
It's an elegant application of basic acid-base chemistry. White vinegar is a dilute solution of acetic acid. Calcium carbonate, the scale, is a base. When you run acetic acid through the system, it reacts violently with the solid calcium carbonate.
That's the foaming and bubbling you see when the vinegar hits the scale.
Exactly. The chemical equation results in the production of carbon dioxide gas, which is the bubbling you observe water, and a new compound called calcium acetate.
And the brilliant part of this reaction is that unlike calcium carbonate, which is stubbornly insoluble,
Calcium acetate is highly soluble in water.
yes, the acid fundamentally alters the molecular structure of the scale. It converts a solid rock that's clinging to the internal plastics and metals of the machine into a highly soluble salt that simply dissolves into the liquid and washes right out the spout.
It dismantles the scale atom by atom.
It's incredible.
But if we connect this to the bigger picture, the ability to descale a small kitchen appliance with vinegar is a minor victory when you consider the macro-level implications of retrograde solubility on industrial and domestic infrastructure.
Right, you can't just pour vinegar into a city water main.
No, you can't. When we look at municipal water systems and commercial boilers, scale is a multi-million-dollar engineering crisis.
And the USGS data highlights the impact on domestic plumbing, too, which is perhaps the most insidious aspect because it occurs entirely out of sight, just behind the drywall.
Completely hidden.
The source material uses a biological analogy to describe the mechanics of scale buildup inside a home's water pipes, which I thought was brilliant.
They compare it directly to atherosclerosis.
The buildup of cholesterol inside human blood vessels.
The mechanics are nearly identical. As hard water continually flows through a pipe, Microscopic layers of calcium carbonate precipitate out and adhere to the interior walls.
Layer by layer.
Over years and decades, this concentric layering gradually reduces the internal diameter of the pipe.
And looking at the physics of fluid dynamics, as that internal diameter shrinks, what happens to the water pressure and the flow rate within the home?
It creates a compounding restriction. The volume of water the pipe can carry drops significantly.
Because the pipe is literally narrower.
Exactly. And furthermore, the interior surface of the pipe transitions from smooth copper or PVC to rough, jagged mineral deposits.
So that roughness introduces turbulence into the water flow.
It does, which increases friction and results in a permanent structural drop in water pressure at the faucet. The pump, or the municipal supply, is pushing the exact same pressure, but the restriction and friction within the scaled pipe sap the kinetic energy before the water ever reaches you.
With the potential for such severe infrastructure damage, we need to establish the parameters here. How does the USGS scientifically quantify when water crosses the threshold from being benign to being a corrosive scaling agent? Like, where are the actual lines drawn?
The USGS utilizes a standardized classification system based on the concentration of calcium carbonate, measured in milligrams per liter, or MgL. It's a highly specific metric.
Let's outline those specific thresholds for the listener so they understand the exact gradients of the data.
Sure. So water containing 0 to 60 milligrams per liter is classified as soft.
Okay.
This water will produce lather easily and leave minimal scale. The next tier, 61 to 120 milligrams per liter, is classified as moderately hard.
Which implies noticeable but manageable effects. But the higher brackets are where the severe scaling occurs, right?
Correct. Concentrations falling between 121 and 180 milligrams per liter are officially classified as hard water. Anything exceeding 180 milligrams per liter is categorized as very hard water.
Wow.
At those upper limits, the scaling and soap destruction are profound. They almost always require mechanical water softening systems to mitigate.
Now, to map where these various concentrations exist across the United States, the USGS relies on a massive aggregated data set. And this is where the methodology becomes incredibly intriguing to me.
Yeah, the mapping is fascinating.
The comprehensive national map of mean water hardness, which is still cited as a foundational text, is based on data compiled by researchers Briggs and Fick from the 1975 water year.
Published in 1977.
Right, as part of the National Stream Quality Accounting Network, or NASQAN. Why is a modern geological survey relying on chemical data gathered half a century ago?
It raises an important question about the temporal stability of groundwater chemistry. In many scientific fields, a 50-year-old data set would be considered entirely obsolete.
Right, you wouldn't use 1975 data for tech or medicine.
Exactly. But geology operates on an entirely different timescale. The Briggs and Fick NASQAN study was an exhaustive undertaking that measured the major ion chemistry of water sources across the entire country.
When you say major ion chemistry, what specific metrics were they analyzing to map this out?
They were measuring the dominant dissolved particles in the water, specifically the major cation, so positively charged ions like calcium and magnesium, and the major anions, negatively charged ions like bicarbonate and sulfate.
Okay.
The critical factor here is that the concentration of these major ions in groundwater is dictated by the chemical composition of the subterranean bedrock.
Right.
Because those vast subterranean rock formations do not change, shift, or alter their chemical makeup on a human timescale, the water slowly moving through them maintains a highly consistent chemical profile year after year, decade after decade.
So the 1975 data remains accurate today because the limestone aquifer sitting beneath the state in 1975 is the exact same limestone aquifer sitting there today, dissolving at the exact same microscopic rate.
Precisely. The USGS explicitly validates the ongoing utility of the 1975 NASQAN data because major ion chemistry in large groundwater systems is remarkably stable.
Short of a massive seismic event that completely reroutes subterranean water flows.
Or severe, unprecedented industrial contamination of an aquifer. But barring that, the baseline hardness of the water being drawn from that bedrock will not fluctuate meaningfully.
However, the USGS does offer a vital caveat regarding the resolution of this data. While the national map is highly accurate on a macro scale, it cannot be used as a microdiagnostic tool.
No, definitely not.
The data illustrates regional trends based on large aquifer systems. It does not account for hyperlocal variations. If you need to know the specific milligram per liter concentration of calcium carbonate at your specific wellhead or municipal tap, you must consult local utility data or conduct independent testing.
That is a necessary limitation of broad-scale mapping. But those broad strokes do reveal definitive geographic realities. The data clearly demonstrates that hard water is dominantly prevalent in the east, central, and western United States.
And that geographic footprint perfectly mirrors the distribution of specific geological formations across the continent.
It does. Those regions are characterized by massive underlying carbonate aquifers, as well as aquifers containing relatively high baseline concentrations of dissolved solids.
Right.
Conversely, regions like the Pacific Northwest or parts of the Northeast, which are characterized by igneous rock formations like granite or basalt, tend to have much softer water.
Because those rocks are highly resistant to being dissolved by weak carbonic acid.
Exactly. They don't give up their minerals easily.
This regional disparity means that industries and homeowners in the east, central, and western U.S. bear a disproportionate financial burden when it comes to water management. They're forced to invest heavily in ion exchange water softeners just to protect their capital investments from scaling.
The economic impact is vast.
But the USGS text actually injects a really great moment of levity regarding the everyday consequences of living in these regions.
It is a rather astute observation about consumer behavior. Because hard water actively degrades the tensile strength of natural fibers due to the embedding of insoluble calcium stearate, and the sheer mechanical friction of the mineral deposits during the wash cycle clothing literally deteriorates at an accelerated rate.
Right, so the researchers posed this humorous hypothesis. Does this mean that high schoolers living in areas with exceptionally hard water are always keeping up with the latest fashion trends, simply because their wardrobes wear out and tear apart much faster than their peers in soft water regions?
It's a great thought experiment. It highlights how a
So what does this all mean for human physiology? We have thoroughly documented the destructive path of hard water. It destroys the surfactant properties of soap. It aggressively scales and insulates heating elements. It permanently chokes off the internal diameter of domestic plumbing, and it shreds the fibers of our clothing.
It sounds like a toxin when you list it out like that.
It does. Given that litany of structural damage, it is entirely logical to question what this dissolved rock is doing to our internal biology. If calcium carbonate scale mimics cholesterol in a copper pipe, is it doing the exact same thing in our cardiovascular system?
And that is the most critical misconception we need to address.
Okay.
Despite the extensive mechanical, industrial, and cleaning-related destruction it causes, the USGS data unequivocally states that water hardness is not a human health concern.
None at all.
There is no correlation between consuming hard water and the calcification of arteries or the formation of kidney stones. Human biology simply does not process dissolved minerals the same way a thermal heating element does.
The sources actually pivot the narrative entirely here. Not only is it not harmful, but the USGS, citing the World Health Organization, points to a substantial physiological benefit.
Yes. The World Health Organization data indicates that drinking hard water can serve as a meaningful supplementary contributor to the required human dietary intake of both calcium and magnesium.
Let's analyze the biological pathway there, because we spend hundreds of dollars on under-sink reverse osmosis systems and water softeners to strip these exact minerals out of the water to protect our dishwashers. But biologically, are those dissolved minerals actually bioavailable to us when we drink them?
They are highly bioavailable. In fact, minerals dissolved in an aqueous solution can sometimes be absorbed across the intestinal wall more efficiently than minerals bound within solid food matrices.
Because they're already in an ionic state.
Exactly. And calcium is fundamental for bone density, muscle contraction, and neurological signaling. Magnesium is a cofactor in hundreds of enzymatic reactions, regulating everything from blood pressure to glycemic control.
So the water flowing from the tap is essentially naturally fortified.
Right.
The earth is preloading the water with essential electrolytes.
Which is particularly vital from a public health perspective. The WHO notes that a significant portion of the global population has a marginal or deficient dietary intake of calcium and magnesium.
Really?
Yes. So for those populations, the daily consumption of moderately hard or very hard water acts as a passive, continuous dietary supplement. It is an evolutionary advantage provided by the local geology.
It is a fascinating duality.
Huh.
We have engineered our modern domestic lives, our washing machines, our water heaters, our espresso makers, around the assumption of pure, inert water.
Right.
And because we built our machines for pure water, the natural mineral-rich water provided by the earth destroys them. It is structurally catastrophic for our appliances, but nutritionally beneficial for our biology.
It exposes a fundamental friction between natural geology and modern engineering. We view the minerals as a contaminant to be eradicated, when in reality, they are essential biological building blocks that our bodies evolved to consume.
It requires a complete reframing of how we view the utility flowing into our homes. To synthesize the USGS data we've covered today, the cloudy film on your glassware and the sputtering of your coffee maker are not signs of mechanical failure or toxic contamination. They are the visible, tactile evidence of the Earth's geology.
It is the universal solvent operating exactly as it should. The water has spent decades slowly dismantling limestone aquifers, carrying those calcium and magnesium ions miles through the darkness, only to precipitate them out onto the heating coil of your kitchen appliances.
It is a nuisance for your plumbing infrastructure, but you can drink it with the full confidence that it is safe and quite possibly actively supporting your physiological health.
Absolutely.
I want to leave you with a final thought to ponder as we conclude this analysis. We have mapped out the entire journey of calcium carbonate, from a subterranean rock formation to the inside of your coffee machine. If water truly is the universal solvent, constantly and quietly picking up microscopic pieces of the earth and carrying them into our homes, what other invisible complex geological processes are we interacting with every single day without ever noticing? We tend to think of geology as massive, static structures, mountains, canyons, fault lines. But geology is fluid, it is dynamic, and it is happening right there in your morning cup of coffee. Thank you for joining us on this rigorous exploration of the data. Keep analyzing the invisible systems that shape your world, and we will catch you on the next deep dive.